to support the loads from beam, from floor, roof, and other area. They are also found as a core and a web member in trusses. So as introduced in previous chapter, compression member usually is subjected to buckling, instability, and material failure. So there are two different failure you can observe in compression member, which is buckling and yielding. So there are two different failure in compression member. Compression member fail due to buckling usually is sudden and dramatic because it lack of the warning of impending failure is a safety concern. So extensive research has been conducted to determine the safe limits on column strength when the buckling is a possibility. Okay, so this is an introduction about the compression member. And the lecture here is based on 13 edition of the manual, especially when we talk about local buckling. We'll follow 13 editions. I believe on 15 edition they do a modification on local buckling issue. But for the textbook that we used in the lecture that we cover, we'll base on 13 edition. So we'll go over that, make sure you understand the local buckling calculation. So I just want to make a note. The local buckling is a little bit different between 13 edition and 15 edition, but our textbook is based on 13 edition when we talk about the local stability. So in the exam, stick to 13 editions method that I cover in class, and also the same as textbook. Okay. Okay, any question for these slides?
No, sir.
Okay. Okay, so in the following sections, we will introduce the basic about buckling behavior and focus on both general member buckling and buckling of sub-element of cross sections. So this one we call global buckling, and this we call local buckling. So global is a member buckling, and local buckling is the buckling of sub-element of a cross sections. So there are two buckling will occur. So this chapter will look at the overall strength of compression member governed by limit states of three different limit states in strength for compression member. So there are material failure, global buckling, and local buckling. So there are three different limit states. Okay? Material yielding or failure, global buckling, and local buckling. So I hope you guys already learned the buckling equation proposed by Euler's equations. in MAE 373. Okay, buckling equations. If not, in other structure classes, you should already cover this. So I don't want to repeat. I just give you the result in here. This is a design class. I'm not going to cover the derivation for this equation. If not, you need to talk to the professor who taught you the class for this equation. So Euler's equation regarding the buckling, sigma critical is a buckling stress. CR here is a critical. Critical buckling stresses is equal to pi squared times E and divided by L over R. The LE here stands for effective length, and divided by R. R is a radius of gyration that we covered before. And L over R, Euler gave a name called slenderness of the member. So LE over R is slenderness of the member. So as you can tell that the buckling strength is dependent on the slenderness of the member, because pi squared is a fixed number. Young's modulus is also a fixed number. Once you pick the material, then the number is fixed. So the buckling stresses, as you can tell, is function of slenderness of the member. So the larger this value, meaning if your member is more slender, then your buckling stresses is smaller, meaning your capacity of your buckling strength is smaller. So when you have a column which is slender or longer, it will be easier to buckle because your sigma critical, the buckling strength or capacity is smaller. Okay? Any questions or discussion on this slide?
No, sir.
Okay? So this is Euler's buckling equation.
Is she sitting right here?
Any questions? No? Okay.
Oh, poor thing.
So, based on the experimental test result, show that Euler's predicted failure loads is rarely attained in real member. The reason is because the compression member usually are not perfectly straight in reality, and there are residual stresses in member that we talk about this in chapter 1 that will create uneven stress distribution, and the end restraint are really perfect pin or perfectly fixed. So the support at the two ends of the column usually are not perfectly pinned or fixed in reality. And also the loads typically in reality is not perfectly concentric, meaning you're creating a moment at the end of the member. So to account for this behavior, compressive strength curve has been developed that skirt the lower bound of compression member strength test data. So the remember of this chapter, look at the limit states that are related to concentrically loaded compression member. So we are not going to talk about when you have moment at the end of the column. So in this chapter, we focus on pure compression member. Okay. Any questions or discussion on these slides?
Other thugs do this, Nia. Why don't you?
What do you
like
mean
do-
by the compression members are often not perfectly straight?
Because in the field, no matter how you manufacture your member, you always have a little bit out of plumbness.
Drink
It
water.
cannot be straight
Go drink water,
because
Nia.
it's human error
Hey,
when you manufacture
go drink
the
water.
member. So theoretically, you assume it's straight when you derive that equation. But in reality, you cannot achieve that
No has comido tú nada, ¿verdad?
due to manufacture error.
Hay quesadilla. Do you want something to eat? I ate some of that
Okay.
fish.
Mhm.
Puse la carne molida. So I can make spaghetti. Yeah? Okay. Which spaghetti? ¿Cómo se dice? The only thing I know.
Any other questions?
Oh my god. My specialty.
No, sir.
Wink wink.
Okay.
Come here. Come here.
So
Come here. Come here. I'll take off the leash.
there are two primary modes of buckling failure may be experienced by steel member.
When are you gonna test me? Huh? When are you gonna test
So,
me? Huh?
The first one we call global buckling.
Oh, you've been not
Another one
running.
we
Have you
call
noticed
local
you haven't
buckling.
even asked for your
So
stupid
as you
phone?
can tell that the
And it's
global
already
is a global
4 o'clock.
buckling,
I told you I could live
and the
without
local
my phone,
buckling
but
can
I
see
don't.
that the whole member is
The world's
okay.
gonna welcome you again.
It's not buckled, but locally
The world is
it
gonna
buckled
welcome
like
you.
that. So this is what we call local,
Gracias, gracias.
and this is what we call global. Okay. So as you can tell that, here I would like to make a note.
Ugh, she's hot. Come here.
So
Yeah. Go under your hair, baby. Go under your hair. Go under your hair. Now I'm gonna go under your hair, bruh. I'm for sure going under your hair.
the buckling directions depends on your radius of gyration direction. We'll talk about that later,
Go under your hair.
real quick. Okay, and this is strong axis on the I shape. Okay, I shape. This is a strong axis, and this is weak axis. Okay, so the Y is a weak axis. So the buckling direction depends on your orientation of your column member when it buckle. It also depends on the support condition at the two ends of the member. So we'll discuss that later in this class, in this chapter. So the buckling direction also depends on your column orientation and also the support condition on the top and bottom of the column. Any questions?
No, sir.
Okay. All right, so global buckling usually is characterized by distorted buckle about the longitudinal axis of the member. By local buckling, the axis of the member is not distorted, but the strength of cross sections is compromised by buckling of a component of a cross sections. So this is global versus local. As you can tell, the global, the longitudinal axis is distorted. Originally is straight, right? But now once it buckle, globally, it distorted like this. But for local buckling, that is straight, longitudinal axis, nothing happened. But locally, it buckled. Locally. So that's the differences between local and global buckling. So when an actually loaded compression member becomes unstable, in an overall sense, we call global buckling, meaning not locally unstable, it can buckle in one of the three ways. So remember, if you want to achieve global buckling,
Is he having a trimmer?
the assumption is that you cannot have local buckling to occur.
Come here, my love.
Okay, if you do have local buckling occur, then usually local buckling will occur first, and then you will occur global buckling. So if your compression member has local buckling, you need to account for this effect into your global buckling strength calculation. So later on in this chapter, we'll talk about how to account for local buckling effect into your global buckling. So if you have a local buckling, once again, local buckling will occur first, and then
Oh, she's still
we'll
having
go
it.
to global. So we need to consider this reduction effect in your global. So let's assume here there's no local buckling. You only have global buckling. So there are
having a
typically
little, no?
three modes of buckling modes. So let me show you the picture first before we go one by one. So this is shown from your textbook. There are three
Come here.
buckling modes. You can see for global buckling. And remember that when Euler developed that buckling equation, he assumed the support at the two ends of the column is pin-pin condition. It's not fixed. He assumed pin and pin. So that's why you see this hollow circle. It's a circular circle stands for pin condition. So this is the assumption that he made on the theory. So what if your boundary condition, your end condition is not pin-pin? Then he also derived other equations for different support conditions. So later on, we will cover how do you account for different conditions at the top and bottom, which is the end of the column. But remember, when Euler derived this equation, he assumed pin and pin support on top and bottom of the member. So here you can see that the first buckling mode you will see is what we call flexural buckling. So this picture is original positions, and once you apply the compression load, it will buckle. So this member, first section right here, will displace to here. So to this dash line. So this is what we call flexural buckling. Okay. So this is very dangerous failure because this happens so quickly. It's sudden. Okay, so you need to prevent this buckling mode. Okay, so if you guys now at home, you can try to grab a piece of paper, or you can grab a ruler, a long ruler. If you guys have that in your home, you can do an experiment. If you try to compress that long ruler, if you have at home, if you compress, you will see the ruler will buckle like this. Okay, so this is what we call buckling, flexural buckling, compression member. If you guys have a piece of paper, you can also imagine that is a column, and then you can try to compress your paper vertically like this way. You can also see the buckling shape like this. So this is what we call the flexural buckling. Another type of buckling is what we call torsional buckling. So if your cross section is like this, is a cruciform shape of the cross sections, then when you compress the member, you will see the pure rotation of the member is buckling. So it's not like you buckle like this. No, it's not. It's actually rotate about the longitudinal axis. So this is the torsional buckling. So this is the second type of the buckling. The third type is you have a channel, compress. So this we call combination of flexural and torsional. So not only have buckling like this, and it will also twist from original to the buckling shape. So this is flexural combined with torsional. So in the IC specification in the manual require analysis of torsional and flexural torsional buckling when appropriate. So in the specification they give you a detailed guideline to deal with torsional and flexural torsional buckling. But typically we will focus on the first type we call flexural buckling. So this is more commonly happen in the structures. Okay, any questions?
No, sir.
No? Alright, so with that being said, let's go back to discussions. Flexural buckling. And it's a deflection
I went through.
or W shape. W shape of the column, for example. And this is what we call strong axis. And this is what we call the weak axis. So typically we call this X, and then we call this Y. So for W sections, you will have Rx, the radius of gyration about x-axis, and radius of gyration about the minor axis. So typically for W shape, the R sub Y, which is about the minor, the weak axis, is minimum compared with Rx. So Rx typically is bigger than Ry for W shape. So the buckling will happen about the smallest radius of gyration, meaning you got the largest of this ratio. So that will be the directions to buckling directions depends on your orientation of your cross sections. And you will buckle about the axis, give you the largest slenderness ratio, meaning L over R should be the largest one. How do you achieve L over R, the largest? Then you need to pick the smallest radius of gyration. So this is the principle you need to remember. So any questions or discussion about these slides? Go ahead.
Can you just stay on this slide for a couple more seconds?
Which one?
I'm still writing some stuff down.
Previous or this one?
Yeah, just on this slide.
The last? Okay.
No, this slide is fine. This slide, yeah.
So you're talking about
Yeah, just this slide. I just need to copy some stuff down.
this one?
No, the previous slide. The one that you were just on. Yeah.
This one?
Yeah.
This one.
No, it was the last one. Yeah, it was that one.
This one?
Yes, that one.
Okay. So any questions about these slides?
No, sir.
Okay.
I have a question, Professor.
Go ahead.
For weak axis, this means it's going to have a smaller radius of gyration.
Yes.
And does it mean that it's going to have less stiffness? Or that
Less moment of inertia. What is R?
R is, it's a function of moment inertia.
Yeah, so it's a smaller moment of inertia.
So with the small I, this means that it's going to have less stiffness, right?
Less stiffness depends on what kind of stiffness you are talking about. If you are talking about bending stiffness, yes.
Thank you, sir.
Yeah, I'm good, Professor. Thank you.
So that's why I'm staying on this slide waiting for you. So I don't know which slide you want me to go over.
No, yeah, you're good. You can go on to the next slide.
Yeah, so that's why I'm waiting here to see if any question. I thought you have a question about previous slide. Any other questions or comments about these slides?
No, sir.
Okay. So Hui, this is the answer for you. You just asked. So range of gyration about x and y axis is defined in here. Okay. So IXX and IYY. So if you say I is smaller, yes, you can say it's smaller stiffness, but in terms of bending, maybe yes. Okay. But usually this is only for cross section property here, so it has nothing to do with stiffness. This only define the cross sectional property. So this is only I over A for is equal to radius of gyration. Second, torsional and flexural torsional buckling we are not going to cover in this class. It rarely happen in reality because we try to avoid these two buckling as much as we could. So typically it will not happen in practice. So we'll focus on the first buckling, which is flexural buckling. So I'm not going to discuss these two in this class. Any questions or discussions?
No, sir.
Okay. Any other questions, discussions? So, let's learn in strength of material, which is MAE 373. The Swiss engineer or mathematician Leonhard Euler, he developed an equation that predicts the critical buckling load for a straight. So here, you assume it's a straight and peak end column. So the buckling load, based on his equation, is equal to critical loads is pi squared EI divided by L squared. Then if you divide by the area of the elements, then that's where you come up with the critical buckling stress. Sigma critical is equal to pi squared E divided by O over R squared. So like I mentioned in the beginning of the class today, the term A over R stands for the slenderness ratio of the member. Any questions or discussions?
No, sir.
Okay. So, if you graphing the Euler's equation, it will show that the predicted buckling stress will become quite large for small value of slenderness ratio. So at this level, the critical buckling stress exceeds the capacity of the material to handle, which is F1. So the limiting strength becomes the material strength instead of buckling when your slenderness ratio become small. So the equation for maximum compressive strength become the minimum of the two, which is either pi squared E divided by L over R squared or Fy. So this is the mathematical expressions. In next slide, I'm going to show you the curve to explain this. But this is the mathematical expression for this buckling strength. So either controlled by the buckling stress or controlled by the material yielding strength, Fy. You cannot bigger than Fy because Fy is the limit. There, you cannot go beyond. So, to explain to you, in the book, they give you this curve, and this curve we call column strength curve. So column strength curve. So as you can tell that if you plot the Euler's equation over slenderness ratio, you will see the curve will look like this. Okay? Which is pi squared E divided by over R squared. But as you can tell that when the slenderness ratio becomes smaller, then somehow the buckling stress FCR is bigger than Fy. So this is not realistic. This is not realistic. So we have to cap or limit this value. So that's why here the limits is up to Fy. Then, for design purpose, the specification create in transition point from Fy in transition to the point where you can continue to use the Euler's equation when you reach a certain point of slenderness ratio. Okay, so the separation point between the two we can discuss later. Where is the separation point of the slenderness ratio that separates the elastic buckling and so-called inelastic?
Shailene, disconnect your thing.
Your slenderness ratio is smaller.
Yeah.
You need to be capped, like I said, by Fy. Then, for design purpose in specification, it proposed a transition line like this between Fy to this point. And then beyond this point, you can continue to use Euler's buckling equation. Okay? So, on the right hand side here, we call elastic buckling. To the left hand side here, we call inelastic buckling. Okay? When you reach inelastic buckling region, we proposed to use tangent Young's modulus. So here we call tangent Young's modulus, which I'm going to talk about in next few slides. Okay, but when you are in elastic buckling, you are using the linear elastic buckling that you typically learned before in chapter 1. Okay, so this is no tangent, and this is tangent Young's modulus. So we'll discuss that later. So usually the elastic buckling will happen for we call stocky or less slender compression member. Okay, and for elastic buckling, typically happen for slender or very tall and long member. So that will be the differences between the two. Okay. So any question or discussion about these slides?
I got one.
Go ahead.
Might sound redundant, but for the FU, is it the compressive stress or is it the tensile stress?
Which one?
Or the FU general?
FU?
Yielding stress.
FY here?
Yeah.
Oh, good point. It's a compression. It's not tension. It's compression yielding. Good point, Hui. It's a compression yielding.
Thank you.
Any other comments, questions, discussions?
No, sir.
Okay. So, based on figure, we just shown that you guys already know. Like I said, the buckling stresses is the minimum of the two. So, depends on which region the slenderness ratio you fall onto. Okay, can be elastic or inelastic buckling. So this is where it comes from. That's from this picture. Okay. Now, before we talk about that, let me give you a quick explanation about the stress and strain curve
Hello?
for compression member. So
Yes,
like
this
you
is
just
her.
mentioned, you just asked. So this is the curve
I'm doing fine. How
for
are you?
typical compression steel
No.
curve. So as you can tell that
Sure.
the initial line in elastic range
Sure. Okay.
is what we call the Young's
No worries.
modulus.
Bye-bye.
So the Fy here is the compression yielding. And when you keep compressing, it will yield, and when you yield, you become this. So the tangent Young's modulus is where you cut a tangent at the yielding point, and the slope is what we call the tangent Young's modulus. Okay, so this is what I just described, the tangent modulus in the inelastic buckling region we just talked about. Okay, so this is elastic, and this is inelastic region. Okay. Any question for these slides?
What is that FPL?
Is the proportional limits. That's where you the limits you become linear elastic range. Beyond that, you start to transition to yielding. Okay. Any other questions, discussions?
No, sir.
Okay. So, let me go back to here. So, what is elastic buckling? Elastic buckling means all the stresses inside the member is elastic. Meaning, for elastic buckling, you are in this range. Okay? But if you are in elastic buckling, and then part of your cross section or member will have yielding stresses occur, meaning you are in this region. For inelastic buckling, maybe it's not purely yielding, but part of the member is transition to yielding. Okay, so that's what we call inelastic buckling. So when you design for taller or slender column, and you would expect that for buckling effect to occur, typically the stresses inside the member are still elastic. So that's what we call elastic buckling. But if your member is more stocky or more shorter slenderness ratio under compression, you will expect that when it buckle, part of the member will already yield or closer to yielding in compression. So the behavior is quite complicated in this region. So that's why to approximate the behavior, we use tangent modulus to substitute into the Euler's equation to approximate the behavior. Okay, so that's the reason coming from this picture. Okay, any questions? comments?
So the y-axis in both those graphs is axial stress.
The axial stresses, yes, in the cross section of the member. So this is stress, and this is strain.
What is
Stress
that?
and strain curve.
What is that unit that it's in?
Which one?
It looks like an F. It looks like a lowercase f. Is that
Lowercase f, like I said in chapter 1, it stands for the demand. Uppercase f is capacity. So this is the demand from the loading you apply. Uppercase f is the capacity that you have for this member, for this material. Any other questions or comments? Discussions?
No, sir.
All right, so let's go back to here. So the early researcher soon found out that the Euler's equation did not give reliable result for stocky or less slender compression member. So the reason is that a small slenderness ratio for member of this type causes a large buckling stresses from typical Euler's equations. So if the stress where the buckling occur is greater than the proportional limits of the material, which is the FPL you guys just asked, the relation between the stress and strain is not linear anymore. So we cannot use the typical modulus of elasticity E. So engineer Engesser, Friedrich Engesser, back in 1889 proposed, then we can just use the tangent modulus in Euler's equation to resolve these problems. So to make the story shorter, the result is this. Buckling loads in elastic region, for inelastic buckling is equal to pi squared et I divided by L squared. Okay, so this is what we just discussed. For if you reach the yielding or closer to yielding for inelastic buckling, then you use ET instead of E in this region. Okay? So any questions, comments, or discussions?
So ET would be a constant, correct?
What's that?
ET would be a constant, correct?
Yeah, ET will be a constant, that's correct.
Thank you, sir.
So that bottom note where it says the stress strain curve shown in figure 4 is different from those in chapter 1. So what exactly, how did it differ from like the previous stress and strain curve from chapter 1? Is it because we accounted for those additional variables of the modulus?
Because for tension, remember what's the tension curve look like? Do you remember? Chris, how does it look like? Do you know? Tension member? Tension test, do you still remember?
Yeah, I think it was like went up and then it kind of like went down a little bit and then it went up again and then there was a fracture.
Like this, right?
Yeah.
So So it's a little bit different from tension because you don't have this hardening region for compression.
Okay, so it's because of the compression we have the other graph instead.
Yes.
Okay.
Mm-hmm. All right. So any other questions or discussions?
No, sir.
Okay, so if not, I think today we already give you a lot of information this time. It's closer to the end. So again, I'll stay here for to answer any question you guys have. If not, again, next Monday is the due date for your homework number 2. The solution will be posted next Monday after 10 p.m. You guys can check the page 4 next Monday. So if not, I will see you guys next week.
Oh, Professor, I did have one question.
Sure.
The Fy in compression value, is that in the steel construction manual?
Yeah, it's the same number as the tension. It's the same number.
Oh, it is. Oh, it's the same number. Okay, I wasn't sure it was the same. Okay.
No, it's the same because tension, compression, the yielding is the same, but the curve is a little bit different.
Okay. Thank you.
Sure.
Is F sub U the same?
Yeah, it's the same. But typically for compression, you cannot go to FU. You only
Yeah,
have
the
one.
FU is only for the hardening region, correct?
Yeah, it's only for hardening. Yes.
And sorry, but hardenings only happen when we put it under tensile stress. Right?
Yes, yes, yes.
These hardening. Does hardening
What's that?
happen? Does hardening happen before necking?
Hardening after, let's see, it's the same time, happen at the same time. Hardening also due to necking, yes.
So, all right.
So if we account for the hardening, are we going to get that first stress and strain curve, or is it going to be a different curve completely?
You're talking about tension or compression?
Yeah, tension.
Tension,
Yeah.
hardening, you have that, like I just drew. You have that
Yeah.
FU curve.
Okay. And then for compression, we're going to have this one.
You only have this.
Yeah. Is there ever a case where we'll ever have like both at the same time, or is that just impossible?
Impossible.
Okay.
Thank you, Professor. See you
Thank
next
you.
week.
Yeah, thank you.
Thank you all.
Actually, Professor, I did have a general question. I've seen in some construction sites where they'll have like a wooden post, like I don't know, like a 6x6 wooden post attached with the steel beam. I was just kind of my general question was, what does that usually do, or does that make it stronger?
No, I don't think it's do anything. I think it's temporary support or something. It cannot be like that. It's useless. Typically, maybe it's just a temporary support.
Gotcha.
Later on, they might take it out.
Okay, yeah, because I saw that.
It's so the timber is so weak, it cannot support steel.
Right, yeah, because it looked like it was mainly like a timber construction project, and then I saw that they had like a steel beam going across, and they had like some kind of timber inside the steel beam. So I was just kind of curious as to what they were doing with that.
No, it's weird. It's no.
Yeah.
I think it's temporary support.
Gotcha. Well, all right, Professor. Thank you so much.
Sure, Chris.
Oh, Professor,
Yeah, go ahead.
I had a question on homework.
Homework? Okay, which one?
Oh, I was looking at the problem 5.
Okay, give me a second.
just a general question. We referenced the gauge table, correct? These are
Five.
our distances between them.
Okay, problem 5. So what's your questions?
So when we reference the gauge table, you have a gauge table in the lecture,
Yeah.
and then and I look at the table on the steel construction manual. They're a bit different.
What different?
For say leg 5, I see the gauge as 3, 2, 2, and then for what I took notes from yours on leg 5, you have 3, 2, 1, 3/4. So
So let me pull out
it's a little bit different, but I don't know.
the file. Okay. Gauge.
In the manual, there's only one table for the workable gauges, right?
Just give me a
Oh,
second. Let's do
stop.
one by one. So
Oh,
your question is
stressed
about
out.
this one, right?
It's sleepy.
Yes.
Right
Okay, which
now,
one I have drawn?
currently, it's
So I
already
used leg 5 because I'm using 2 holes, so minimum.
This one, 5?
Yeah, G1 and G2.
Uh-huh.
Their G2 in the book is 2.
Here it says 2.
Yes,
And how about this?
that's 2.
2 and 2?
Mm-hmm.
In which book?
The 15th manual.
Oh, in manual.
Yes.
Let me check. What they say? Is there any other differences in here? How about the 6? Are they the same or different?
Let me see.